Has anyone in here ever written some C# code? C# programmers? Good. Come on in. All right, and has anyone written an async-await in your C# code? Yeah, right, this is bread and butter. We do it all the time, every day. We've probably written thousands of them. So I have a little confession. About a year ago, I was writing my 10,000th async-await, and I was like, you know, I don't know if I actually know what this is really doing. I had sort of like a crisis of faith. And I went through kind of a personal journey of digging in and understanding it, and I was really surprised at what I learned. So now I'm going to take you through the speed run version of my journey through this, and maybe I'll get to surprise you, and maybe you'll learn something. Or maybe you already knew this, and you'll be like, wasted 25 minutes. Anyway, so wait what Async-Await explained. First, just a couple quick acknowledgements. I want to dedicate this to my dad, Larry Hess, who passed away this year at age 83. I really lucked out in the dad department. Thank you, Daddy. He was an amazing man, amazing father. I want to thank CG Infinity, my employer. They're here in Plano, super supportive of these kinds of activities. Really a very enlightened, great place to work. We're doing a little recruiting these days, so CG Infinity, you should look it up. Okay, so the first thing I want to do is ask a question. What is the point of async programming? Why do we even do this? So basically, async, we want to allow our code to do more than one thing at a time, to walk and chew gum, right? We just don't want to like sit in one place. We'd be like, okay, start that and do something else in the meantime. Now, that style of programming has lots of names and jargon around it. People talk about parallel programming, concurrent programming, multi-threading, come on in, hey Ron, asynchronous programming. So these are all different kind of nuances and flavors of doing more than one thing at a time with your code. So the async version of that, it focuses on letting your code stay busy or responsive while you're waiting for a longer process to complete. You've kicked something off and you just want to stay busy. Okay, it's a little different than maybe parallel programming or some other things, but that's the emphasis. So that's very abstract. So let's bring it into the real world. Let's say that you are in Kyoto and you're hungry and you want dinner. So if you're going to get dinner in Kyoto, you're going to walk into one of a million cool little cafes, and there's going to be one of these kiosks. Maybe if you've been to Japan, you've seen this. You walk up to the thing, you make your selection, you put in cash, totally cash-oriented culture, no swipe and stuff. And it makes a little ticket, and then the guys in the kitchen get your ticket, and they make your dinner. Okay, so that's how you're going to get dinner in Kyoto. But let's say, just hypothetically, stick with me here, that you're also thirsty. You don't just want dinner, you'd like a drink. So, while the guys are cooking your food, you walk out the door down the street and you find one of the 10 million vending machines, drink vending machines that line the streets of Japan. You put in your 100 yen and you get a bottle of happiness, okay? Then you walk back down and you sit down and you enjoy dinner in Kyoto. So there are two ways you could implement this in code. The first one, this UML sequence diagram shows you the synchronous modeling of this interaction. First, my function, which is called getDinner, calls order food. And then it waits for the food. And then once it's got the food, it calls getDrink. And it gets the drink. And then you sit down and you enjoy your dinner and your drink. That's synchronous. Okay? And this is generally a waste of time. This is not what we want. What we want is overlapped, right? Asynchronous processing, where you put your money in the machine, in the kiosk, you order your food, and then while they're cooking it, you go and you get your drink, and then once both have completed, you sit down and you enjoy your drink. So that's what async gets us. That's what we're trying to solve. So let's write it in C#, okay? Let's just port that all, slam it right on into C#, see what it looks like. So I'm going to take you through this a little slow because the devil's in the details here. Can everyone see the text okay? I can try to, no, that didn't work. I don't know if I can. Okay, we're going to have to work with it. Okay, so we have our static HTTP client instance. Here's our main function, async task, get dinner in Kyoto. And it's going to await, order, drink. It's going to order dinner, await, order, drink, and then it's going to enjoy the dinner and the drink. And these are just the supporting functions. Order dinner is a REST API call to some server called restaurantkiosk.com, where we specified item 29, and the option was rice. And if we got that back, we deserialized our dinner JSON, and we returned it. And then similarly, here's a drink. We order drink, it's the drinkmachine.com, item 7. And if the REST API call came back, we're like, cool, get me the JSON, deserialize it, and then we can enjoy dinner and drink, right? Okay, quiz. Which UML sequence diagram does that implement? The first one, sync, or the second one, async? It's covered in asyncs. What is it? Which one? Synchronous, synchronous. Anybody else want to vote? Okay. It is the synchronous implementation because when you call await in C#, the code doesn't advance to the next line until the result comes back. I don't want to say blocking, because blocking is a term that smells like threading, but it basically is in this weird suspended state until you get the next one. So when I first saw this, I was like, wait, what? WTF? Why are we even doing this? What is the point? What does this buy us? Right? That was the kind of crisis I had, the wait what moment. It's like, it is not doing what I think it's doing. I almost started going back and just ripping this stuff out and being like, I'm going back to synchronous. I don't want this, because it's a lot of work. So, okay, so we're going to dig into this, and the rest of the talk is explaining what it actually does and why you do need to do Async-Await. But before that, I do want you to know that I ordered the chicken pork katsu. It was really good. Okay, so, sorry? Oh, yeah. I mean, that's like regular Japanese. Japan is full of amazing, amazing food of all kinds, but like working person food, like after a hard day and you're just hungry, pop into a kiosk, cheap, get a giant plate of pork cutlet smothered in curry and call it a day. So, okay. So what does Async-Await actually do? It's all about the thread pool. So I'm going to walk you through this. So in reality, your C# thread pool has tens of thousands of pool threads. But let's just imagine that you've got a C# Lite, okay, and they only gave you 3 threads. So we've got this sad little thread pool that contains exactly 3 thread pool threads. And you've written a server here, and whenever a request comes in, your server is going to start running some code, a task. Service that request. Well, as you may know, when you program in tasks in C#, you are given a thread pool thread. Okay, tasks run on thread pool threads. So what happens is T1, the first one, gets assigned to your task, and it starts running. Step 1, great. Step 2, great. And step 3 is the thing that's kind of slow, right? Maybe the call out to the REST server, something like that. So that one is kind of busy there, right? It's kind of, in computer terms, it's stalled out. And then 2 more requests come in. Okay, great. Thread 2 gets assigned, T3 gets assigned. They all zip through step 1 and step 2, and now they're all kind of holding out there on step 3. So what happens, see you, Rahul, have a good one. What happens if a 4th request comes in? Got a problem, okay? This is called thread starvation, right? Request 4 is out of luck. It cannot even start until a thread is assigned. So this is the problem that Async-Await solves, thread contention, right? Competition for a limited resource, the thread pool. So let's go back in time. When that first request is serviced, and we call it as a task, and we await it rather than just executing the task, what happens is When it gets to step 3, which is the awaitable step, the C# runtime creates what's called a continuation. That's your vocab word for the day, a continuation. And a continuation, you can think of it like a special bookmark, okay? So C# says, okay, that line of execution, that call stack, I'm gonna bookmark it right there. The thread goes back to the thread pool, and I'm just gonna listen for a magic signal that tells me, hey, you could rehydrate that one and pick up where you left off. So it lets the thread release and go back into the thread pool. So now, if you've got these 3 requests and they're all async awaited, all the threads are there, and when your 4th request comes in, hey, happy day. We have a thread pool thread available to service it. So that's what Async-Await actually does. Now, just to complete this story so you have a full mental picture of like the life cycle, let's say that that magic signal happened. Ding! And what that means is that for the request 1, it got the result of step 3, and now it's ready to move on. Well, so the runtime says, oh, great, we can continue. It clears the continuation, it grabs another thread pool thread, and it lets your code continue on. One really important fact that I illustrated here is the thread you started on may not be the thread you continue on. There's no thread affinity between a thread pool thread and a task. And if you have, like me, ever written multi-threading code that uses things like thread static, which creates affinity between variables and threads, you're hosed when you port it to this. It's really disastrous. So that's kind of a detail, but it's important to note that any thread that your task is running on, it'll change around. And you can do some tracing and see this. It's really cool to see how the system is allocating threads. Okay, so in summary, Async-Await, just on its own, does not let your code perform multiple things in parallel or overlapped, okay? That's not its purpose. What it does do is it frees up thread pool threads so that your server, your process overall, can be responsive and service many tens of thousands of concurrent requests. Now, I have an unproven hypothesis that the reason this is in the C# language is because the ASP.NET team had created this train wreck. They built ASP.NET servers that all of a sudden were maxing out the thread pool, right? And they're like, oh heck, what do we do? Oh, well, let's just change it all over to Async-Await, and that way our ASP.NET servers don't bog down, and then it's propagated out, right? Because for a normal small app that isn't servicing tens of thousands, it probably doesn't really matter that much. But we are all writing code now that gets executed in the cloud, in Azure Functions, in Azure Services, and we should assume that in the background it is all running in Docker containers on Azure Kubernetes service, like it's all running in this highly shared environment, and we have no idea what the hardware resources are. So we have to use Async-Await and play nice, because the people running that infrastructure assume that we are. Okay, so we have to do this, even if you think your app is kind of small or silly. Okay, so I have 11 minutes left. I want to just go through a couple of implications and analyses. Now, I've got a longer version of this talk if you're enjoying it. It's posted to my YouTube channel, and I dig into a few more weird nooks and crannies. But for 25 minutes, we had to edit it down a little. So the first thing is, what if you did actually want dinner in Kyoto implemented asynchronously? Like, because all of you are like, that's what I want to do. How do I do it? So there's simple C# code to do it. You just have to write your C# a little differently. You have to say, okay, the way we implement it is we create the task. Dinner task equals order dinner. Got that task. Drink task equals order drink. Notice that we did not await them individually. And then we say await task.whenAll. And we hand it the list of tasks we're going to await. So you can tee up 1,000 tasks and just await all. And while you're waiting for them, your line of execution is not holding on to any threads at all, right? It doesn't matter how long those take. Eventually, they'll come back. So that's the proper overlapped, right, asynchronous implementation. This is a great technique. Okay, so if you take away a vocab word, it's continuation, and if you take away one code snippet, that's your code snippet. So the other thing, this is a little theoretical, but it's fascinating, and it kind of blew my mind. What makes something awaitable in the first place? So just going back to CS 101, you can talk about I/O bound versus CPU bound work. Okay, CPU bound work is work that relies on a core, on a processor, and that's usually very math intensive, and you really are limited by the computation resources you have available. So building an LLM is a classic example of CPU bound work, and that's why it takes so many processors to do that. But other things that I've done, like nonlinear regression or giant matrix multiplication for supporting flow cytometric compensation, like sciencey, mathy stuff, tends to be very core intensive. I/O bound work is stuff where you're waiting on a port, usually, possibly a file. Right? In the old days, it was more file I/O. We don't do as much of that anymore. Where basically you've sent a request out over a port and you're kind of waiting for the result of input-output. And if you probably can't read all these, but these are like a whole smattering of C# namespaces and functions that are awaitable. For example, in system.net.http, you have HTTP client get async, HTTP client patch, HTTP client post. In Microsoft Data SQL client, you've got execute reader async or read async. Or in system.io, there's the file ones. In Azure Service Bus, you've got service bus sender.send message async or service bus sender.receive message async. And other weird ones, Windows storage, named pipes, cryptography. So what do these all have in common? They're all port operations. They're all I/O. So the magic, the common thread is things that you actually await are I/O. So you remember way back when I was going through the steps of the thread pool example, and I said that the system makes a continuation, which is a bookmark, and then it listens for that magic signal. Okay, what is the magic signal? How the heck does this work? You know, so the magic signal is provided by an operating system level function that in Windows is called IOCP, IO completion port. This is a low-level Windows function, right? You access it only through the Windows API. What this means is that the C# runtime is doing the pinvoke, right, API work for you, and it basically works like, hey, Windows, I'm going to make a port request. I'm going to subscribe to this other port. You signal me when my first request is done. I'm subscribing to the completion port. And then Windows will say, hey, man, ding, your thing's ready. C# picks that up, clears the continuation, gives you a thread pool thread, and off you go. So it's crazy to me that this whole framework is built upon this very low-level Windows operating system function. It's implemented, has different names on Linux and iOS, but they all support this concept. So in summary, Async-Await doesn't do what I thought it did initially. Are you surprised? Maybe. Anybody here surprised? A little bit? Yeah. It uses IOCP and continuations to free up thread pool threads when doing lots of I/O-bound work. And this allows a high-performance app to service many clients. You can still run tasks in parallel, but you have to use waitall, a task.waitall. One of these bullet point work, these last two ones are the implications that I edited out. So I'm summarizing something that I didn't talk about. The sync async boundary and handling CPU bound work. So if those sound really fascinating to you, you can follow up by connecting with me on LinkedIn, going to my YouTube channel. There's a long form version of this talk plus 60, 70 educational tutorials on all kinds of things, Azure Service Bus, test first development, and I'm wearing different really cool shirts in all of them. So if all you want to do is appreciate my really fun shirt collection, you can do that. So honestly, that would be great. I'd love to get a few more followers and subscribers, and if you do all those likey, subscribey things, that's awesome. And if you do feel the need to communicate via email, I occasionally check C# Artisan hess@gmail.com. All right, so there you go. Async-Await explained. We have just a couple minutes if there's a comment or a question. Or just shock and awe. Yes, sir. You had a question?
No, just shock and awe.
Shock and awe. Okay, thank you. Right on. You guys have been great. I hope you have a wonderful conference.